Good evening. Good evening. So this is the last lecture in this series about graphs and knots. And we already discussed graphs, we discussed spanning trees, we discussed how to draw a diagram of a knot or link having plane graph, but we never reached really kind of our goal, the picture which was always here as the symbol of my talk. This here you have triangle. On the triangle we did draw trefoil knot using our construction, but now you see this triangle has three colors. Maybe I'm not that visible, so I will draw one small, the red color, then the blue color, and finally the yellow one. I hope now it will be visible. So later I will describe precisely this construction, but just say quickly, we see that at every crossing three different colors here meet. So this Fox, we call Fox tree colorings, was devised by famous American topologist, not theorist, Ralph Fox, and I will talk about this, but first some history. So Ralph Fox did PhD in Princeton in 1939. He was doing initially some general topology, Lusternik-Schaldeman, properties, etc. But then he became very much interested in knot theory, and he became kind of the leader of world, and in particular American knot theory. So what about this Fox tree colorings? So Fox, as I said, was professor in Princeton. He was in Princeton and then professor in Princeton, essentially all his life. But here he had sabbaticals. As we know, in America there are sabbaticals. So in 1956 he got sabbatical and he was teaching in Haverford College in Pennsylvania. And when he came to this college, he wanted to teach knot theory, but he realized quickly that what he wanted to teach is too advanced initially for students. So he didn't know abstract algebra, for example. So he decided to teach them initially at least knot theory from very, very elementary point of view. And for this purpose, he devises this Fox coloring. It was some method of coloring which kind of could distinguish different knots, and in particular trefoil knot from trivial knot. So this is about Fox, and I will make precise rule of Fox colorings later. Crowell, Richard Crowell, was student of Fox, and Richard Crowell, with Fox, they wrote very basic but very important fundamental book on Introduction to Knot Theory. This book is mentioning Fox coloring, but only in exercises. This book is very famous. So, for example, I have here translations into Russian and Japanese of this book. Japanese and Russian translation. This Fox coloring was so elementary that it was taught in many more elementary settings, like for high school or middle school. But this will be later. And finally, what about Hale Trotter? Trotter was really is universal mathematician. He's still in Princeton, retired professor. And in particular, knot theory, he's very well known that if you consider knots, they can have orientation, direction. So Trotter was the first person who proved that exists a knot which is different than the same knot with different orientation. So by deformation in space, you cannot change one orientation into another. But what about Fox colorings? So Crowell was giving talks to teachers and teaching them about Fox colorings. And then he was thinking, can you generalize from 3 colors to n colors? And I always thought, and other people as well, that it was Fox really who defined n colorings as well. But in this article of Crowell for teacher, he writes that it was really Trotter who gave him idea. So I asked Trottel how it was, and Trottel saying, I don't remember well, I think it was Crowell, but maybe if Crowell says so, it was in our joint discussion, and colorings were defined. Maybe in this talk I will be unable to make precise definition of n colorings. In fact, it's not so easy without much knowledge to generalize from 3 to n. But let's do first formal definition. So I erase blackboard. So we can continue with defining Fox tree coloring finally. Of course, it should look somehow like this tree coloring of Fox. So what are the rules? First, let's think about this as a rule of childish game. So we have diagram of a knot, and I will not draw diagram, just crossing. And rule of the game, you can think they are children and they have some drawing, and then rule of the game. Rule is either such crossing has only one color, this is allowed, you can say it's plain, but it's allowed, only one color. Of course it may be red, blue or yellow, or at a crossing we have all 3 different colors, never 2. So here, for example, I can choose red, I can choose, for this blue, and I can choose here yellow, so it's supposed to be yellow. So this is a rule of the game. We have diagram, and we can only color using these rules. So let's see once more how it was for trefoil knot. I will draw this trefoil without supporting triangle. So we try to color this, so we can choose arbitrary color here. So there are 2 choices now. Either continue in red and everything be red. If everything is in one color, we can call this trivial Fox colorings. But we look for non-trivial. Trivial always exists. So we have to change color. So for example, I draw this blue. And finally, I have to change color, so this is yellow. And it works. Clearly, trefoil knot has non-trivial Fox colorings. So, what are these colorings good except play of children? In fact, there are already booklet produced when you just, task of the children is to find coloring, Fox tree colorings of given diagrams. But really, Fox made this construction for this undergraduate student because using Fox colorings we can distinguish knots. How we distinguish knots? I would say that we count how many different Fox coloring has given diagram, and then argue that if you choose different diagram, deform our link, so we can have different diagram, then this number will be unchanged. We call this invariant of a knot or a link. So Fox was arguing that this can be used to distinguish trivial knot from trefoil knot. And this is the beginning, then you can make it more advanced, but this is the beginning of very nice and useful knot story. I was telling that this Fox invented for his students in Haverford College. In fact, mathematics of this was known to famous German mathematician Rademeister and them much before. But their definition and their construction was very complicated. Instead of Fox coloring, we'll have representations of the fundamental group of the knot complement or link complement in the space into dihedral group of 6 elements. So for this undergraduate student and for most of us, almost every term in my slogan is difficult to understand. Particularly, we need this fundamental group, knot complement, 3-dimensional space, etc., etc. But with such a game, it is relatively easy. So to have just some notation, and one more thing which was kind of natural here is that when you color arc of the knot and we go over crossing, we don't change color. There's no abstraction, so we have to use one color. We have to change color, we can change color only when you have something like this. So I said the rules, I will write them informal rules. At a crossing, either one color or all three colors are used. So maybe to illustrate what about three colors and still non-trivial Fox coloring, let's slightly change this note. Let this note be like this. Diagram, of course, like this. This is legitimate Fox colorings because at every crossing either three different colors are or just one color here, yellow at this crossing. So this is legitimate. So now how to formally say what is the number which will distinguish notes? It is numbers of Fox colorings. Let them know this number, colorings using three colors of the diagram. So this is the number of different Fox colorings of given diagram. It's the number of Fox colorings of a given diagram of D. So let's try. Our kind of local goal is to say that as long as we believe that this number is unchanged when we change diagram, we don't change link or not, but we change diagram, so we deform link in the space, we put in different position, but link is the same, but diagram can change, then this number is unchanged. This for a moment you should believe. So with coloring diagram, what we can observe easily. So if we take the number of Fox three colorings of the trivial note, just circle, there are only trivial colorings. It may be red, it may be yellow, or it may be blue. So this is just three. What about our trefoil note? Maybe I should not try to draw him trefoil too often, but okay. So what is the result here? First of all, we can use just one color, like here, this white is here. So this trivial colorings. How many trivial colorings? Three. It may be red, blue, or yellow. So we have three trivial colorings. So this number corresponds to trivial colorings. Okay, what about non-trivial colorings? As this picture, or rather, this picture is showing, there is non-trivial coloring. And this is one of example, but we can change blue, yellow, and red, kind of permute them. So how many possibilities? We can put here any color, not only red, but yellow or blue. So we have three choices here. When we already draw one, we have to change color, so we have two choices, and the last is compulsory. So it's just 6. So plus 6. So the answer is 9. Just to pay attention a little, 9 is square of 3. So let's try some other examples. And for example, figure 8 note, the next note we have. So let's draw figure 8. Not remember it was coming, maybe I should remind you the construction from cone using our construction. I will not do this by red, let's do this by white color. Remember, the rule was bridge on the left. Let's connect this. This is figure 8 knot, or foil 1 because I need some notation. Foil crossing, the only knot of foil crossings. So how many colorings it has? 3 coloring of our, I will write foil 1 without trying to draw. Of course, we have trivial colorings. We can just use one color. Everything red, everything blue, or everything yellow. So it is 3. Now, let's look for a non-trivial one. So let's try. First arc may be arbitrary. So let's do this red. We can notice that if you choose here red as well, then everything will be red. So let's change our color. Here, blue. Blue. Okay. What next? We have to change color. For example, in this crossing. So this should be different color, yellow. Okay. Here we have to change color. This should be red. But if I do this red, I have something already wrong here. We are blocked. And we will be blocked in all other attempts because this was pretty general attempt. I took arbitrary color here, arbitrary different color here. I was forced to have yellow here. Then I was forced to have red here. Contradiction. There is no non-trivial Fox colorings. So this will be +0. So this is just it. So let me write comment. No non-trivial Fox coloring. Okay, so what are conclusions? Remember, these conclusions are that number of Fox colorings is independent on how we put our knot in the blackboard. What is the diagram of the knot? If you put like this or totally different, the result is the same. This has to be proven. But if you believe it already, then we proved that trefoil knot is non-trivial. What about figure 8 knot? We don't know. Number is the same, but of course Fox coloring is not universal thing. But you can make some conclusion. Figure 8 knot is different than trefoil knot. How to distinguish figure 8 knot from trivial? Maybe not in the stock, we need 5 colorings. But now let's make short discussion. So this is pretty good tool of distinguishing knot, but of course not universal, but nice play, because here you can use actual colors. Already from 5, the rules are more complicated, more algebraic. And I will finish my talk with these rules. But now, what about why I am saying that by deformation of the link, changing diagram, this coloring is preserved. This requires some history. So, when you do diagram, we have very concrete kind of projection of our link into the plane, keeping over order, but very concrete. So what happened when we deform something in space? And in fact, it was already Maxwell who in his notebook made the following pictures. So Maxwell, him, friend of Tate, very much interested in knots, but never published about knots. So, what was his observation? Another obvious observation would say that if I have a small piece of a knot, this is, I draw only this, what is it? Then it's not important. I can make kink. Like this. The rest is the same. This is different diagram, but clearly the same link in the space, the same knot or link in the space, because I can just make it straight. This is just like making from this piece of knot, making this. Of course, in space, I can do this without cutting or gluing. What he drew as another option? Another option is that you have 2 pieces. So we have 2 pieces of our diagram, and then we just put one above another. And finally, Maxwell drew the third picture. When you have already 2 pieces of rope, crossing, you can have the third one going on one side to another. Just different drawing, but the same link. So practically what it means that we have this on one side that we move to another side. So this move, and this move are clearly not changing the link in space, even if diagram is changed. Maxwell didn't publish anything, so there was no, in his time in 19th century, any method of proving, because what we say that if you make kind of natural deformation of the link in the space without cutting and gluing, we claim that the diagrams, maybe they are different only by these links. This in fact is theorem, but proved only in 20th century, in 1928, so much after Maxwell, but German mathematician Rademeister, I was already mentioning him. So he proved that really two diagrams represent the same link in the space, so from one diagram to another you can go by deformation in space, really if they differ by a finite number of such moves. So this is Kurt Rademeister. And the same year, this result was proven by American mathematician J. Alexander in the paper with his student Rix. However, these moves are called Rademeister moves. First Rademeister move, second Rademeister move, and the third Rademeister move. It's obvious why they are not called Maxwell moves, because of course Maxwell didn't prove anything and even didn't publish. But why not Alexander? My feeling is that Rademeister paper is very clear, very precise proof. When Alexander Blick's paper is a little hand-waving. Some details are omitted, is correct, but some details are omitted, is much more difficult to understand. So these are Rademeister moves. So this theorem, let's write it formally. Two diagrams represent the same link if they differ by Rademeister moves. Two links, two link diagrams represent the same link Remember, link is something that we allow deformation. So these two diagrams are different presentations of the same link if they differ by a finite number of Rademeister moves. So, using this theorem, we can prove that number of Fox coloring is unchanged by Rademeister moves. I will show just one example, but really pretty nice. So let's erase Rademeister move. I will in a moment draw one of them. So I like have bigger one. So we try to prove fact. Let's write fact. The number of colorings, three colorings of the diagram, is unchanged by Rademeister moves. This result by Rademeister moves. So it means that this number of colorings can be used to distinguish knots. So how we check this? We just check that there is bijection, that the same number of colors are before move and after move. Of course, with such colors, there's plenty to check. In fact, it's a very nice exercise, not difficult to check Rademeister move. Kind of the most difficult, it looks like being the third Rademeister move. I will draw this kind of linear, it would be easier for me to do something. So. Okay. So this one side, and now I take this bottom line and move to other. now first crossing is this, and the last crossing was moved here. So what I mean, I don't like to make precise proof, but more or less what means that if you color this diagram, I have unique coloring of this diagram, Fox coloring. If I color this, I have unique coloring here. So this is how it looks. So many cases, but let's start from the case that this is red, this is yellow, and this is blue. So first we recognize that if you've already chosen these arcs, then the rest goes automatically. For example, blue is on the top, so go to this. Yellow goes over and ends here. Red goes here. Now, when I have coloring, this should be blue. Now, remember about other rule. If I have already two blue, the last one should be blue. And because these are different colors, this should be red. So, this is have chosen red, yellow, blue. This is automatically done. When the number of coloring here and here will be the same, when I have this bijection, when I start with the same colors here, coloring this, which is unique, I will end with the same colors outside. Inside it will look different. That's nice. So let's color this. We don't know anything, so this was red, we go here, this was blue, goes here, no, it was yellow, goes here, and finally blue goes all the way through. Okay, at least this one is okay. Now, here I have to change color to red. Here I have to change color to yellow. And here I have to change color, so must be blue. So you see, there are two colors blue, but still this and this are the same. This is graphical proof that Rademacher move in this special setting is giving bijection between colors. So I will not consider other cases, but it proves in particular what we stated before, that trefoil knot is different from trivial knot. So now, just for conclusion, how you can guess what is n colorings? You cannot. So it's not so easy to guess. In fact, this is what telling me always my friend from Poland, Witek Rosicki, that one day I was describing Fox tree coloring. So he asked me, what is n coloring? I said, I don't know. Next year I already wrote paper, and this is kind of my first paper about Fox tree colorings, first paper, when I already described n colorings, because you have to go from colorings like for children into small algebra. So what is the criterion for our tree coloring from algebraic point of view, and what it really means, tree colorings? So let me erase this picture. So maybe to do it quickly, what is the condition? What are tree columns? You can say that we work with group Z3. Work modulo 3. So there are three numbers, 1, 2, and we work modulo 3. So there are various possible of writing rules corresponding to three different colors and the same color. I will choose the rule which generalizes immediately. However, I said that it's not the most natural rule. So what is the rule? If this is A and this is B, what should be C? C will be 2B minus A. We can see that if all colors are the same, or maybe write equivalently, 2B is equal A plus C. Of course, if all colors are the same, this holds. If all colors are different, it's like 0, 1, 2, modulo 3, it works. Remember, modulo 3. So, what is the natural generalization? And you can check by yourself that it works. We can work generalization, Fox n colorings, Fox n colorings. We work with Zn. And the rule is the same. 2b, let me write equivalent to a plus c, but this time modulo n. It is a very nice exercise that if you consider all colorings satisfying this rule, it will be preserved, number of n colorings will be preserved by Rademacher move, and is much stronger invariant. As I mentioned, figure 8 knot can be proven to be non-trivial using